Okay, so if you need help calculating in general wavelength and frequency, remember I do have another video specifically on that. This one is going to look at more so energy of photons, but we're going to get into some basic calculations of frequency and wavelength down here. But know that there is another video to help you if you are struggling with the initial setup of, or the idea of what wavelength and frequency are and how to fill in that equation. But for this one, this is problems 5 and 6 on the homework sheet as promised. So let's just dive right in. Let's look at some of these formulas up here. So when we look here, this is going to be energy is equal to H, remember, is Planck's constant, provided right here in joules times seconds, is equal to Planck's constant times the frequency right here. We can also use this particular equation. So energy is equal to Planck's constant times c, which is the speed of light. Here, in most of my equations, I'm going to use 3 times 10 to the 8th, so see that it's just the rounded version of this. Meters divided by seconds. And why I would use this one over this one, again, it depends on what the question provides you. This is just a manipulation of this because we know that frequency is equivalent to speed of light divided by wavelength. Makes sense? So it depends on what the problem gives us. So other things we might need are some of our conversion factors. So right over here, 1 meter is equivalent to 1 times 10 to the 9 nanometers. And 1 nanometer is equivalent to 1 times 10 to the negative 9 meters. The beautiful thing about the metric system is we can just move some decimals, okay? But units are very important here, and you'll see that in some of these problems where we have to do multiple conversions based on what they've provided and what they want their answer in. So let's just dive right in. Question number 5, it says the energy of a mole of photons of red light is 175 kilojoules per mole. Calculate the energy of 1 photon of red light. What is the wavelength in meters? And then it wants us to calculate it in nanometers. Okay, so big picture. Let's just start looking at some units that I see here, just to kind of like break down this problem right here. I see a mole of photons. Remember, we know 1 mole of anything is equivalent to 6.02 times 10 to the 23. Right? So if you have a mole of puppies, you have 6.02 times 10 to the 23 puppies. So here, if we have a mole of photons, we have 6.02 times 10 to the 23 photons. Okay, so this right here that we have been provided is how much we have in 1 mole. It just wants 1, right? So that's just an easy conversion. If I have 175 kilojoules per 1 mole, well, for every 1 mole, I have 6.02 times 10 to the 23. So, if we were to plug that into our calculator, again, these are going to, mole is going to cancel here. Mole is going to cancel here. My answer that I get when I plug it into the calculator Alright, so notice this is in kilojoules, and all the formulas that we're going to be working with, and like for example Planck's constant has joules. So I want to do a really quick conversion here. So if this is in kilojoules and we want to get it to just joules so that our units match up nicely, okay? So 1 kilojoule, if you think about King Henry died by drinking chocolate milk, we have kilojoules. We want just joules. That has no prefix, so it's a base unit. So we need to move the decimal 1, 2, 3 times to the right. And if you're thinking about this in terms of the exponent, that means this is going to be converted to 2.91 times 10 to the negative 19 joules. Okay, so far, so good. So this is how many joules. This is how many kilojoules is 1 photon. This is how many joules of 1 photon. So these are equivalent, they're just different units. Then it says, what is the wavelength in meters? And then it wants me to do another conversion and calculate nanometers. Okay, so because it's asked me for wavelength, let's look at these 2 equations. Okay, this one has wavelength as a variable, so I just need to manipulate this equation to position this right here in this spot. So whenever we do manipulate that, the new equation that we get, or like maybe I was writing a different, yeah, okay, I'm going to alternate between red and green. But the new equation that we get is going to be wavelength is equal to Planck's constant times speed of light divided by the energy. Okay, so this is really just a plug and chug based on the information that we just saw for and the constants that we already have. Okay, so wavelength equals Planck's constant, 6.62 times 10 to the negative 34. Make sure that you're writing the units so that you can see that they cancel. Again, this is why we did this conversion right here, because of the joules right here. Times speed of light. Again, I'm just going to round this to 3. That will be sufficient. Meters per second, which I'm going to just change to S negative 1. That's basically, remember, if you'd say negative exponents, because they just took it out of the denominator, made it a numerator. Divided by, and then the energy. You just calculated this, okay? That is this number. Okay, so if we are solving for wavelength here, the only unit that should not cancel is meters. So if we set it up perfectly, every other unit should cancel. I have here, okay, and I'll just go back to red. I'm just going to leave these pins open. Okay, so I have joules on the bottom here. I have joules on the bottom there. They cancel. Here, remember, this S would have been part of the denominator. Okay, so it would have canceled if it was on the bottom, but it's also, whenever you have two exponents, right, you just add them. So 0, and then the, or I'm sorry, this is the 1 right here. 1, and then negative 1 cancels out to 0. These units cancels. The only one I have left right here is the meter. Now, if this were a multiple choice question on the AP exam, we could do some quick math by just reducing the exponents, and that would help me eliminate some options. But if this were on the free response, obviously you could just put it all on the calculator. But whenever I do put this all in the calculator, it is going to be equal to 6.83 times 10 to the negative 7 meters. Okay, so this is my first answer. Okay, so this, well, actually, this is my first answer. So this is the first part of the question. This is the second part of the question. My final question, now it's just asking me to convert this that I have here into nanometers. So that's where we have to use these conversion factors. Okay, so I'm going to rewrite it down here. I guess I'll do it in red. I'll just like alternate. So 6.83 times 10 to the negative 7 meters. Remember, for units to cancel, whatever you have on top, that unit needs to go on bottom. So here, if we have one for every 1 meter, I have 1 times 10 to the 9 nanometers. Okay? So 6.83 times the 1 here, so that's still 6.83 times. The base is still 10. When you are multiplying exponents of the same base, you add those exponents. So negative 7 plus 9, this is going to give me a positive 2 nanometers. Okay, this is the same thing. This is in scientific notation, but that is the same thing as saying 683 nanometers. I would accept either answer. Okay. So that one's good to go. I answered all 3 parts. Now, down here at the bottom, this one's actually much easier. It says the most prominent line in the spectrum of neon is found at 865.438 nanometers. Other lines are found at 837.761 nanometers, 878.062 nanometers, etc., etc. Part A, it says, which of these lines represents the most energetic line? Okay, so remember, that's where we have to understand the relationship between energy, wavelength, and frequency. So if my wavelength is shorter, okay, so if you can imagine my wavelengths here, let's draw, I'm going to draw some wavelengths here. Okay, so if I have shorter wavelength, it means I have higher frequency, which means greater energy. Longer wavelength, less frequency, because remember that inverse relationship, it's also less energy. So when it says which line represents the most energetic line, I'm looking for the one that has the shortest wavelength. Of my options provided, that would be my answer. Then it says, what is the frequency of the most prominent line? Well, my most prominent line, they already told me, most prominent line, so 865.438 nanometers, okay? So if we were looking at frequency of the most prominent line, frequency, I'm going to just like write some down here. Okay, so frequency, V, is equal to speed of light divided by wavelength. Okay, so we're just going to literally plug and chug. 2.998. Oh, I told you up there that I was going to use 3, so I'm going to just carry that out to the same thing. Let's do 3.0 times 10 to the 8 ms negative 1 divided by the wavelength here. It has given me the wavelength in nanometers, which means I need to convert this. So the exact same thing that happened up here. Okay, but instead this time we need 1 nanometer on bottom, which means that we're going to be using this. So 1 times 10 to the negative 9 meters. When I change this to scientific notation, if I were to put it in the calculator, honestly, you can just carry it down like this. For math's sake, it would be 837.761 times 10 to the negative 9 meters. And again, we did that so that these two units would cancel. When I put that into the calculator now, I would get 3.464 times 10 to the 14 s negative 1. Again, this is the unit for frequency, this or hertz, Hz, whichever one. Alright, so then it says what is the energy of 1 photon of this wavelength? Okay, so we have frequency here that we just calculated, so we can just use this equation here. So E is equal to Planck's constant J times S. Okay, and then we are going to multiply by the frequency. So I'm running out of space here. But this is time, so like this is division, sorry. This is multiplication. Times our frequency, which is this right here that you just calculated. When we do that, 2.295 times 10 to the negative 19. S negative 1 and S are going to cancel. We're left with joules, which is good because that is what energy is measured in. Alright, let me know if you still have questions.